Hello my dear students, welcome to my channel Dey Sir's Chemistry Coaching. Let's start expected questions and answers of your coming board exam on coordination compounds. Do you know what are double salts? Let's understand. A double salt, actually it is a crystalline form of two salts with some water molecules as water of crystallization. Okay, so a double salt is a mixture of two different salts with some molecules of water as water of crystallization. The best known example is carnallite and more salts. Carnallite has composition potassium chloride, magnesium chloride, including 6 molecules of water, and more salts. This is very important for your practical also. That is ferrous ammonium sulfate. Ferrous sulfate, ammonium sulfate with 6 molecules of water. What is the characteristics features of a double salt? When a double salt is dissolved in water, say consider a double salt is taken. If you add water, it is soluble and breaks into constituent ions. So when carnallite is dissolved in water, it gives the identification test of potassium ion, it gives the identification test of chloride ion, it gives identification test of magnesium ion. That is, it dissociates completely. So it is said that when a double salt is dissolved in water, it loses its identity. Thus, a double salt its identity in solution. Thus, a double salt loses its identity in solution. That is, there is no existence. It completely breaks. Another compound is ferrous ammonium sulfate called more salt. Whenever it is dissolved in water, it gives the identification test of ferrous ion, sulfate ion, as well as ammonium ion. Thus it is said that a double salt is a crystalline form of two different salts with some molecules of water as water of crystallization. When a double salt is dissolved in water, it breaks completely to give the identification test of corresponding ions. Coordination compounds. You know, whenever any compound is dissolved in water, the left side possesses positive charge and right side possesses negative charge. So when this compound dissociates, left side always possesses positive charge and right side always possesses negative charge. Remember this thing, okay? Whenever this compound is dissolved in water, the left part, it is a bracket part, it does not break at all, okay? The left part becomes positive charge and the right part becomes negative charge. That's why this complex, this part, the bracket part is called complex. This complex is called cationic complex. Whenever this compound, that complete is called compound, the bracket part is called complex. Whenever this compound is dissolved in water, left side becomes positive charge and right side becomes negative charge. That's why it is anionic complex. If you consider this compound, in front of the compound nothing is there, back side also nothing. So whenever this compound is dissolved in water, it does not break at all. This is the neutral complex. No cleavage. So I think you understand it. So let's understand different parts of a coordination compound. In the complex part, there is one central metal ion. Other than central metal, the rest called ligands. Total number of ligands is called coordination number, and outside the bracket, that's called ionization sphere. Actually, whenever a coordination compound is dissolved in water, it gives the identification test of ionization sphere. Ionization sphere, complex part, there is no ionization sphere, okay? Now, next question is, what are coordination compounds? So listen, coordination compounds are those in which a central metal is coordinately bonded with ligands. When a coordination compound is dissolved in water, it does not lose its identity. It means, listen, say this compound when dissolved in water, now it breaks into only two parts. Left side, you know that it becomes positive charge, and right side becomes negative charge. This part, the complex part, does not break at all. So this compound when dissolved in water, it gives the identification test of only chloride ion. This compound gives the identification test of only chloride ion. So the main difference between a double salt and coordination compound is that a double salt when dissolved in water breaks completely and loses its identity, while a coordination compound when dissolved in water does not lose its identity. We get the identification test for coordination compound only the outside part, not the inside part, okay? The inside part is called coordination entity, this part, complex part also, okay? So I think you understand it. So the question is, what are ligands? What is the denticity of a ligand? So what are ligands? Ligands may be charged ions, positive or negative, or neutral molecules which donate a pair of electrons to the central metal to form coordinate bond. There are some ligands which form only one coordinate bond with the central metal. They are called uni or monodentate ligand. There are some ligands which form 2 to 6, 2 or 3 or 4 or 5 or 6 coordinate bond with the central metals. They are called multidentate ligands. 2 means bidentate, tridentate, tentadentate, pentadentate and hexadentate. So let's understand. A ligands are charged ions, positive or negative, or neutral molecules having lone pair of electrons. Negatively charged ligands, chloride, bromide, cyanide, isocyanide, etc. There are another also. Positively charged ligands, NO2, positive charge on nitrogen called nitronium ion, NO, positive charge on nitrogen called nitrosonium ion. And the examples of neutral ligands are ammonia, water, pyridine, symbol is PY, formula is H5N. So these are the ligands. These are all mono or unidentate ligand because they form only one coordinate bond with the central metal. There are other ligands, they can form 2 to 6 coordinate bonds with the central metal. They are called polydentate or multidentate ligands. Depending on the number of coordinate bonds formed by a ligand with a central metal, that is called denticity of a ligand. So what is denticity of a ligand? It is the total number of coordinate bond forms by a ligand with the central metal. I repeat, denticity of a ligand is defined as the total numbers of coordinate bonds formed by a ligand with the central metal. If a ligand forms only one coordinate bond, that's called uni or mono. If a ligand forms 2 to 6 coordinate bonds with the central metal, they are called poly or multidentate ligands. Elliptic and heteroleptic complexes. Listen, this is the complex part. Inside a complex, if the central metal is bonded with only one kind of ligand, that's called homoleptic complex. And if the complex contains two different type of ligands which are coordinated to central metal, then that complexes are called heteroleptic complex. I think you understand it. This is the complex part, okay? Only one type of ligand called homoleptic complex. If there are two or more different type of ligands called heteroleptic complexes, okay? Heteroleptic complex. Now you know that in this chapter, IPC naming is very important thing. During IPC naming of coordination compounds, remember these things. The IPC name of coordination compound is applicable only for complex part, not for ionization sphere, whether it is back side or it is front side. So remember it, the IPC naming for complexes is applicable only in case of complex part. During IPC naming, you should determine the oxidation state, you can say valency, of the central metal ion. That is the first stage. The oxidation state in the IPC name should be written in Roman letter, not as 3, 4, 5 Roman letter, okay? There are three types of complexes, you know. Cationic complex, that is the complex part at the left hand side, and ionization sphere, these are all cationic complex. Anionic complex, complex part right side, in front of this anything is there, that's called anionic complex. You know that this is anionic complex, okay? You know that this is anionic complex, that is complex part in the front or the complex part back. This is anionic because whenever it breaks, positive, negative, so it is anionic complex. And another is neutral complex, that is there is nothing outside or inside. The first IPC rule for cationic and neutral complex. So let's start the IPC naming, okay? If you consider this compound left side becomes positive charge and right side becomes negative charge whenever it breaks. So it's a cationic complex. Whenever this compound is dissolved in water, you know that left side becomes positive charge, so it's a cationic complex. It is a neutral complex because there is nothing front or back. In case of cationic and neutral complex, at first determine the oxidation state, that is valency. You know that during the formation of this type of complexes, central metal sometimes releases electron from the valence shell. That is actually oxidation state or valency. How to determine the oxidation state? Listen, these are all neutral complexes because nothing is mentioned, no charge is mentioned on these complexes. So these are neutral for neutral coordination compounds. These are neutral coordination compounds. In case of total is called compound. In case of neutral compounds, what is the rule to find the oxidation state? I think you know. The sum of oxidation state, that is the valency, is equal to 0. How to find it? Listen, we have to calculate the oxidation state of chromium. Say X plus 6 into ammonia. Any neutral complex has charge 0. Any neutral ligand has charge 0. So it is 0 plus, you have to calculate it also, 3. Chloride, any halide, chloride, bromide, iodide, fluoride, they have charge -1, you know this. -1. Total is neutral, the compound equal to 0. Therefore, X equals to +3. And you know that the oxidation state is written as Roman. So what is its name? During the naming, IPC naming of complexes, only remember it. The IPC name, only the complex part is used, not the whole. So it is ammonia. So there are 6 ammonia. So hexamine. The IPC name of ammonia, don't forget to write 2M. Hexamine. Chromium is the central metal. Now write the oxidation state, Roman, under bracket, and at last write the simple name of the ionization sphere. The IPC name for this not applicable. IPC is only applicable inside the bracket, so it's a salt, or remember it. Don't write any number, don't mention any number here, so it is only chloride, because the salt of chlorine called chloride. Don't mention any number. How do you write? See, this is heteroleptic complex. In case of heteroleptic complex where there are different ligands, write their name in alphabetical order. This is amine. This is pyridine. So A comes first, then this. So how many? 4 numbers. So tetra, amine, di or bi, di, pyridine, then the name of the central metal, chromium, oxidation state. How to determine? 0, 0, it's X, it's -3 equal to 3. So you can write directly X -3 equal to 0, X equals to +3. So it has also oxidation state 3. 3 and chloride. It's a neutral coordination compound. The rule, you know that. At first write the number of the ligand, then name of the ligand. 4 tetra carbonyl nickel and What is the oxidation state? X plus 4 into carbon monoxide. It's called carbonyl in IPC name. Acts as neutral ligand. So 0 equal to 0. Therefore, X equal to 0. So nickel has oxidation state 0 here. That you have to mention. So remember it. During the IPC naming of cationic or neutral complex, at first write the number of the ligand, then name of the ligand, then name of the central metal, write the oxidation state under bracket, and at last finally write the ionization sphere. Don't write any number of ionization sphere. Directly it's a salt of chlorine, that's chloride, such as sodium chloride, potassium chloride, like that. IPC naming is only applicable inside the bracket part, that is a complex part. In outer part, no IPC naming is applicable. When there are different types of ligands, write their name in alphabetical order. If the oxidation state is 0, you have to mention it. Okay? This and this. For multidentate ligands, you know that from bidentate to hexadentate, they are called multidentate ligands. For multidentate ligand, write bis, tris or tetris instead of bi, tri and tetra. Also write the name of the ligand under bracket. So listen, understand the examples. These are uni or monodentate ligand. This is a multidentate ligand, ethylene diamine. Charge 0, 0, 0. These are all neutral ligands. At first, determine the oxidation state. X plus 0 here minus plus 3 into minus 1 equal to 0. Therefore, X equals to plus 3. So here cobalt has oxidation state of 3. If you consider here, it's 0 because it's a neutral bidentate ligand. One ethylene diamine makes 2 coordinate bond with the central metal. So X plus, this is 0, so 3 into minus 1 equal to 0. Therefore, X equals to plus 3. So here also oxidation state of cobalt 3. These are both multidentate, not multidentate ligands. These are unidentate ligands. So write direct number. You know that when there are ligands, write their name in alphabetical order. So it is amine, it is nitrosyl. Okay, it's a neutral ligand. So triamine. Always write the double M. Nitrosyl, IPC name of NO. Cobalt, under bracket 3, at the end bromide, not tri, not di, nothing, only bromide. This is a salt, bromide. Here you know that ethylene diamine is a bidentate ligand. So don't write tri, write tris. And also write the name of the ligand under bracket. Actually, En is called ethylene diamine. But whenever you write the IPC name, don't write its IPC name at ethylene diamine. Nowadays, it is better to write ethane 1,2-diamine. Cobalt 3 bromide. One interesting thing is that, listen, whenever you write the IPC name of ammonia, you use double M. But whenever you write the IPC name of En, you use single M. That's, remember it, don't get mistake. That's a very important. In case of ammonia as ligand, its IPC name write 2M. In case of IPC name of ethylene diamine, write single M. Okay. Now, I think you understand it. In case of IPC name of negatively charged complex, that is if the complex is at the right hand side, only the difference is that write 8, ATE8 with the name of the ligand, write 8 with the name of the central metal, okay, write 8 with the name of the central metal. Others rule are same. So let's understand it. Clear? Say these are the examples. K4 FeCN whole 6, K3 FeOX whole 3, these are negatively charged complex because the complex part, that is bracket part, is at the right hand side. Whenever you break it, it becomes positive and the complex part becomes negative. That's why negatively charged complex. What is the rule? In case of negatively charged complex, only write 8 with the name of the metal. Write 8 with the name of the metal. For negatively charged complex, write 8 with the name of the metal. Okay. For negatively charged complex, write 8 with the name of the metal. So the rule is that for negatively charged complex, write 8 with the name of the metal. Name of the metal, okay. For negatively charged complex, write 8. Now, at first find the oxidation state, that's the necessary, of central metal, say it is X. How to find it? For potassium, listen, lithium, sodium, potassium, rubidium, cesium, they belong to group 1, that's they have valency +1. So 4 into +1 plus X to be calculated plus 6 into cyano. Each cyanide has -1 charge, therefore X equals to +2. So the iron has oxidation state of +2. Here 3 into +1 plus X plus 3 into oxalate. You know that oxalate, this is oxalate ion, COO minus, COO minus, this is oxalate ion, and so its charge is -2. So each oxalate ion has charge -2. Sometimes it may be written as ox, or sometimes it may be written as C4O2, this C2O4 -2, okay. This is oxalate ion. So this is a bidentate ligand. You see that each ion makes 2 coordinate bond. So it is -2 equal to 0, therefore X equals to +3. So it has also iron 3. So how to write the IPC name? At first write the ionization sphere which is at the front, potassium, don't put any number. So only write potassium, then write the number, it's a unidentate, so hexacyanido. Cyanide has IPC name cyanido. Iron, but it's a negatively charged complex, so don't write iron, rather write ferret, FeRrAt, ferret. You see that in case of negatively charged complex, add 8 with the name of the metal. ferrate, and at last the oxidation state, that is 2. Here it's a bidentate ligand, remember it. So in case of bidentate ligand you can't write tri, rather tris. Also write the name of the ligand under bracket. So potassium tris oxalato ferrate 3. So I think you understand it, okay? So these are very important IPC naming. I think these are important for your forthcoming board exam. At first, write the oxidation state of the central metal. Another thing is that see, directly charge is there mentioned -2. So it's a negatively charged complex, that is with the name of central metal you should write 8, that is cobaltate. This is thiocyanate. Whether it is cyanide or thiocyanate, charge is -1. So x plus 4 into -1 equals to, you know that for charge complexes the sum of oxidation state is equal to the charge. So it is -2. Therefore x equals to +2. So here cobalt has oxidation state of 2. 4 tetra thiocyanide. It's a negatively charged complex, so cobaltate two. Directly ion is given, you can write cation, anion or ion. Anion. Better to write anion, or simply you can write ion. So this, you see, this is the complex part is at the left side, so it is cationic complex, direct only cobalt. Do you know what is it? It's ethylene diamine. It's a bidentate ligand, and you know that in case of bidentate to hexadentate, you should write the name of the ligand under bracket, and instead of 3 write tris. Ethane 1,2 diamine, only write single M. Cobalt, it's a positively charged complex, so cobalt, what is its oxidation state? X plus 2 is there, so 2x plus 0, because it has 0 neutral ligand, 0 charge, plus 3 into, you know that each sulfate has charge -2, 0, therefore x equals to +3. So here cobalt has oxidation state of 3. At the end, this is a salt, don't mention any number, so it's simple sulfate. Here left side positive, right side positive. So this part is cationic complex, this part is anionic complex. In case of cationic complex, write the name directly. In case of anionic complex, add 88 with the name of the central metal. How to find the oxidation state? Just consider x and x in both of the cases, because the density of the ligand is 2 and here also 2. So the coordination number in both of cases same. That's why write X plus 2 into, you know that ammonia has 0 plus X plus 2 into cyanide has minus ion equal to 0. Therefore, X plus X 2X 2. So X equals to plus 1. So this silver has 1, this has also 1. How to write the IPC name? Listen the IPC name, okay? Di or bi, diamine write double M, okay? In case of ammonia, write double M. In case of ethylene diamine, write single M. Silver 1. Then write the name of this. Dicyanido. You can write bi also, okay? Argentate. One. Okay. Argentate 1. 8. Why? Because it's a negatively charged complex. It is in right side. How to write the name of this? Sodium. You know that sodium, potassium belong to group 1. So each has oxidation state of plus 1. So 3 into plus 1 to be find out the oxidation state of aluminium plus X plus this oxalate ion. Each oxalate ion carries minus 2 charge. 3 into minus 2 equal to 0. Therefore, X equals to plus 3. So aluminium has oxidation state of 3. Listen now, the complex part is at the right hand side. That's why aluminate. So sodium, never write the number in outside, only write the name. Sodium tris, because it's a bidentate ligand, so instead of tri, tris oxalato aluminate. Three. I think you understand it. So for this year, one very important question that may come in your board exam, that is Warner's coordination theory. Warner's coordination theory is only applicable in case of coordination. Understand Warner's coordination theory. It states that in a coordination compound, a central metal shows two different types of valencies. Number 1, primary valency, which is actually the oxidation state of metal, which is ionizable. Number 2, secondary valency, which is actually the coordination number, which is non-ionizable. For example, this is a complex. What are the primary and secondary valency? At first, determine the oxidation state of central metal. X plus 3 into, you know that each oxalate carries minus 2 charge. What is the rule to find the oxidation state for complex or for charged complex? The sum of oxidation state is equal to the charge. Therefore, X equals to minus 3 plus 6 equals to plus 3. So iron has oxidation state of 3, and you know that oxidation state is the primary valency. So the primary valency is 3, that is oxidation state. What is the secondary valency? Secondary valency is the coordination number. You know that each oxalate ion makes 2 coordinate bond with the central metal because it's a bidentate ligand. So if each oxalate ion makes 2 coordinate bond, so 3 makes 6 coordinate bond. So the secondary valency is 6, that is coordination number. So I think you understand it, okay? Now do another very important board question. Determine the primary and secondary valency, okay? Let's understand the question. Determine the primary and secondary valency of this complex. Determine the primary and secondary valency of the complex, that is determine it. Fe EDTA charge -1. Find the primary and secondary valency. Primary and secondary valency of the central metal iron. At first calculate the oxidation state X plus. You know that EDTA is a hexadentate ligand. Each EDTA carries charge -4. So iron has oxidation state of 3. So the primary valency is 3, that is nothing but oxidation state. And secondary valency, each EDTA, this is very important for your board, remember it. Each EDTA makes 6 coordinate bond with the central metal. So the coordination number of iron is 6 here. So the secondary valency is 6, because as EDTA is a hexadentate ligand. So I think you understand today's topics, okay? Thank you for being with me. Please do subscribe my channel so that more and more videos will reach to you, which are very effective for your board exam. Thank you.